Hello, my name is Steve Kim. I'm the Director of Product Marketing for Cable TV and Broadband Products. This presentation will introduce you to our new MTTplus-522 module, which we call the OSP Plus Expert Module. It is designed for the telco outside plant. The agenda is as follows. I will provide you an overview of the product and its key features and applications. So let us begin. The MTTplus-522 is comprised of key copper line test plus G.fast DSL CP modem emulation. The main features are a digital multimeter, a time domain reflectometer, a resistance fault locator, PSD or power spectral density, background noise, longitudinal balance, impedance detection, voice frequency noise, insertion loss, which is done with a far-end device, and DSL XTU-R, G.fast FTU-R modes based on a Broadcom chipset. The test ports are as follows. For copper testing, there are 5 2mm mini bananas. They are color-coded as follows. For pair 1, tip array is black, ring or B is red. For pair 2, tip is blue, ring is yellow, and green is for ground or earth. For G.fast and DSL, there's the RJ11 port. And lastly, there is an Ethernet port for DSL pass-through mode. The digital multimeter is made up of a DC voltage meter, DC current, resistance, ground resistance, leakage, capacitance, and AC voltage. Some of the main applications for DMM are to measure cable balance. This can be done using both capacitance and resistance. Estimating the length of the copper loop. This can also be done using capacitance or resistance. Using the resistance meter to ensure proper insulation/isolation resistance between tip A, ring B, and earth ground. And lastly, simple fault identification, such as detecting a short or foreign battery on the copper pair under test. For the DMM, we've also implemented an auto test, which is comprised of the main DMM measurements for all 3 legs, tip, ring, and ground. So the auto test will take you through DC voltage, AC voltage, capacitance, a loop length estimate based on capacitance, capacitive balance, isolation or leakage resistance, and lastly, loop resistance. The TDR, or time domain reflectometer, is a very powerful tool to locate and identify faults. There are 3 examples shown in this slide. The far left is an open circuit at the far end, which is shown by a pulse that goes upwards. In the middle is showing a short circuit. That is a pulse that goes down. And the third is a bridge tap. Classic shape being a downward pulse followed by an upward pulse. You can see with the bridge tap, you can take 2 markers and place them accordingly to determine the distance to the bridge tap and the length of the bridge tap by placing the 2 markers where they are, and you can see the delta distance. Within the TDR, we've also implemented a impedance mismatch detection function, which will report the presence of various impedance mismatch events. PSD, or power spectral density, background noise, is essentially a field spectrum analyzer. It can be used to measure the presence of noise on the copper pair. Now, this could be induced crosstalk from neighboring copper pairs that are in service. It can be due to AM radio perhaps stations that are nearby, etc. So it's a powerful tool to see noise that may be present on the copper pair. The concept of cable balance is very critical for the copper pair's ability to be immune to crosstalk. Interference or noise is a common mode, or what they call a longitudinal signal. When there's enough degree of imbalance between tip and ring, for instance, capacitively and resistively, this can result in crosstalk arising for the copper pair. Longitudinal balance is another measurement technique used to quantify the degree of cable unbalance. The way it does this, it transmits a common mode test signal along the shield of the cable to simulate interference. And then it measures the resultant differential signal across tip array and ring and B, and reports this signal in units of dB. Now, for a voice band longitudinal balance signal, the typical pass limit is greater than 60 dB. So longitudinal balance is another way to assess cable balance. RFL, or the resistance fault locator, helps to determine the distance to resistive faults that are not easily detectable by a TDR. The way an RFL works, it requires a shorting strap or a far end device to provide the short at the far end. The way it works is you connect to a known good conductor, or two if available. You connect also to the suspected conductor that has a fault, as well as the third conductor that's connected to that fault. So simply you follow the connection diagram that's presented on the test set. You short appropriately per the connection diagram at the far end using either a shorting strap or a far end device. And when you start the measurement, the RFL will yield the following: an estimated distance to the fault, a distance to the end of the cable or the strap, and the distance between the strap and the fault to help sectionalize where the trouble may be. Impulse noise is a transient or short duration burst noise that can cause transmission errors, but it's very difficult to detect with a spectrum analyzer. So impulse noise is a time domain based measurement used to detect impulse, and it's presented as an event counter or an event graph. As mentioned, we've developed a far end device which we are calling V-Fed. Its primary function is to provide a shorting function for RFL and the resistance meter to measure loop resistance or loop length. The Fed is also the way to send signal from the far end to the MTTplus-522 for it to measure insertion loss or frequency response. So it's a signal generator for the MTTplus. As you can see, it's a standalone box. It's battery operated. DSL and G.fast. Over the many years, we've seen the evolution of residential DSL to G.fast. As you can see, from ADSL to VDSL2 to now G.fast, you can see that the copper loop is just getting shorter and shorter and shorter. And by doing so, this allows the bandwidth deliverable over the copper to get higher and higher. G.fast is transmitted on the last 100 meters of copper. In essence, it is a fiber to the distribution point technology. And because the copper loop is so short, you're able to utilize much higher frequency, and thereby G.fast can yield up to 1 gigabit of transmission data rate. The test features offered for G.fast DSL is CPE mode. It is based on the industry-leading Broadcom BCM63138 chipset. This has the maximum interoperability with the predominant DSLAMs out in the market today. The 3 modes supported are G.fast FTU-R. It is compliant to the ITU-T standard for G.fast, which is G.9700, 9701. The initial release for G.fast supports a spectrum up to 106 megahertz, and there is now a 212 megahertz version of G.fast that has been recently released. VDSL2 FTU-R mode is supported for all profiles, 8 megahertz, 12 megahertz, 17 megahertz, and up to 35B. It is also compliant to the vectoring standards, 993.5, and G.IMP retransmission standard, G.998.4. Legacy ADSL ATR is also supported. This is for Annex A ADSL over POTS only. Lastly, all of this testing is for a single pair only. The main application is your traditional classic plug-and-play DSL G.fast layer 1 turnup. Upon achieving showtime with the far-end DSLAM or G.fast DPU, the test set will present key metrics, including the achieved current rate, the maximum obtainable rate, the capacity, the SNR margin, attenuation, etc. There's an icon indicator where green indicates the modem is in showtime and red indicates no connection. For the carrier tones, there are nice graphical presentations for bits per tone, SNR per tone, H-log, which is essentially an insertion loss frequency response curve. This is powerful in that it can show the presence of bridge taps if the insertion curve is not smooth and there are dips. And lastly, for DSL, we have basic IP connectivity test to support ping, traceroute, and web browser. And if you have any questions, please contact me. I thank you for your time today.